All right, picking up after that rather abrupt stop, I had to answer the phone. I want to do the algebraic way, and then I want to show you a simulation that hopefully might be more convincing of how we look at the standard deviations in these two cases, where we either play it 20 times for real or we just play it once and then fake it by multiplying by 20. So here's the fundamental law for standard deviations is that it's a Pythagoras-like law, that the standard deviation of a sum of independent variables, okay? Now we really need independence. Is the square root of the sum of the squares of the individual standard deviations. It's almost nicer to say this in terms of variances. It just says the variance is the sum of the variances. But I want to focus on the standard deviation here. Okay, so we know the standard deviation of each of the individual scenarios. That was equal to here, $5. Okay, so we're just going to put that in. It's the square root of, okay, $5 squared is 25 plus 25 plus 25 plus 25. And how many of them are there? There are 20 of them. And so I'm going to get, let's simplify that. Let's just take out the root 25, because that's actually very relevant. So this is equal to root 20 times $5. Okay, the $5 was the individual standard deviation of each one, and we're seeing that it's multiplied by the square root of 20. Now, if we want a number for that, we can go ahead and calculate. Actually, it's probably not going to like the dollar sign, so let's just have it calculate that numerically. It's about 22.36. So $22.36 is our new standard deviation. That's a measure of the spread of the winnings over the 20 plays of this game. Okay. Now, what if I did the fake? Okay, so this was, let me just make it clear. This was scenario 1, and then scenario 2 was where I played it once and then faked it by multiplying by 20. Well, here the rule is much simpler. It's just that if I have a certain random variable and I scale up the value, if I just, instead of reporting what the value is, I multiply by 20 right before I report it, I just multiply the spread, the standard deviation, by 20. Okay, that's easy. That's 20 times $5. And of course that's $100. That's a lot more variation. So this is where we get to one of the punchlines here, is that scenario 2 is a lot more variation. And how much more? Well, let's see. This, let me just say this in one other way. 20 is the square root of 20 times itself. Oops. Times the square root of 20. And it was that square root of 20 times $5, which was the standard deviation for scenario 1. Okay, so this is the square root of 20 times the standard deviation from scenario 1. That's a pretty hefty margin. It's really not even close. That this is a lot more variable. So this is something I think we need to justify a little bit more. But I just want to repeat: if I add a bunch of independent random variables, I actually get a lot less variation than if I just scale up that random variable by that same number. They have the same expected value. Remember, they both on average gave me 100, because this was just 20 copies of something that gave me $5. This is 20 copies of something that gave me $5. But these guys are independent. These guys are really just the same one answer multiplied by 20. So let's look at a simulation over here in Fathom to see if we can get a little more intuition for this. I'm going to start with scenario 2 because it's a little bit simpler to explain how Fathom does it. 50 times, I went ahead and did 50 trials. I just played the game once and then multiplied it by 20. Okay, the numbers are probably pretty small on your screen, but these are 10s and zeros. These are 200s and zeros. Okay, and I just did a dot plot of the outputs. Okay, about half and half, zeros and 200s. Not exactly half and half, because this isn't exactly going according to what the probabilities tell us. It shouldn't. It's a simulation. And notice there's a lot of variation here. And in fact, the standard deviation, this number here, the 99.7, is the standard deviation as calculated for this particular sample. And that's very close to the 100 that's predicted from scenario 2. And so notice what's happening is it's all or nothing. Because I can either just win or not, there's nothing in the middle. There's no intermediate values when I just take the prize and I just multiply it by 20. The average, the mean here is 116. Notice it's not exactly 100, which is what I would expect, but it's pretty close. Okay, so now let's look at what happens if I do the more complicated version. So here, over here where it says collection 1, I've got 20 coin flips, and I look at all the prizes, either 0 or 10, and I add them up. And where that goes is it goes into this sum over here. So these are the actual sums that we're interested in. So what I did, the reason there's 5 here so far, is what I've done is I've done this simulation randomly 5 times, and it's going to re-randomize each time, and I'll show you a few more in a minute. And at each time it calculates the sum. And notice I'm getting numbers like 80, 90, 120, 160, somewhere in the middle between 0 and 200. It's extremely unlikely that I would get either 0 or 200 here. Very different from the case with scenario 2. Okay, so I've got some of the summary statistics. We can just check. The prize, it's calculating the mean is around 5. The standard deviation is around 5, as we predicted, for each individual prize. Okay, and so far we've got some statistics for the sum. But let's get a bunch more cases of this. 5 trials is not a lot of trials, so I'm just going to collect more measures. And as I do that, I'm building the dot plot of all the possibilities. And notice what I'm getting. I'm not getting anything way at the left at 0 or way at the left at 200. I'm getting a lot of cancellation. Yes, I'm going to win some and I'm going to lose some because they're all independent of each other. There's no way they're going to be all zeros or all tens because they're independent, and it's very unlikely that they would all come up by random chance the same answer. Notice that scenario 2 is essentially doing this where it can only be all zeros or only be all tens because I took the 0 or 10 and I just multiplied it by 20. Here I get a lot of intermediate results. Let me just go ahead and add a bunch more at a time. So I added 10 there, added 10 again. And so I'm building this dot plot that is a lot less spread out than the dot plot of the fake version, the scenario 2 version. Let me just do a couple more. Okay. So that we want to compare that dot plot with this guy. That is an extremely spread out thing. If I can only have values between 0 and 200, this is as spread out as I can get. It's only zeros and only 200s. This one, it doesn't even touch 0 or 200. It's just, that's so unlikely. I would have to run a lot of simulations to get even close. Maybe run a couple more and see if I get lucky. Nope. It's really unlikely to get even like 10, 20, or 180, 190. I get a nice curve in the middle. And in fact, what I claim is it's going to approach a normal distribution, which is a pretty huge theorem in statistics. But we're not getting there yet. Let's look at the stats here. 99.38. Okay, so on average, I'm winning $100. That was our expected value. And look at what this standard deviation is, 22.8. That's getting pretty close to the prediction of 22.4. Okay, so this is a very important thing about statistics. It was when I've got independent random variables and I sum them up, the sum is not nearly as variable as if I just took one instance and I multiplied it by 20. Another way to say that is that the 20x is basically as if I added 20 different dice rolls, but they were the exact opposite of independence. They were exactly correlated. They always either were all tails or all heads. And that's going to give us an all or nothing scenario, nothing in the middle, and much more variation.